Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. And we're in chapter 1, part of this playlist called Probability. And let's jump to today's topic, which is calculating the mean number of rolls in craps. Craps is a dice game that we introduced in ims10. So the 10th video in this playlist. I think it was independent events or something like that. But this is a random topic. And after ims10, we calculated the probability of winning the game craps, and I decided to calculate the mean number of rolls in a game of craps out of just pure curiosity, no other reason. And then the derivation ended up being pretty cool. So then I have to share it. So let's go through this. So the game of craps is on the first roll, you roll 2 dice and you let the sum of the 2 die equal t, and that's actually called the point. So we win if the point is 7 or 11, and we lose if the point is 2, 3, or 12. If it's not one of those, we go on to roll 2. We pick up the 2 die and roll them, and we continue to roll until we observe our point or a 7. We win if the point is observed before a 7, and we lose if a 7 is observed before the point. The number, and the point again is the first number that we rolled in rolling the dice. So find the probability Pn that the game stops after roll in. And we'll just kind of go through this incrementally until a formula emerges. So when n equals 1, the game stops on roll 1 if the point is in one of these 5 numbers, 2, 3, 7, 11, or 12. The game instantly stops and you either win or lose. And there's a 1/3 chance that that happens on roll 1. Now remember, we're not calculating, that number of rolls to win or the number of rolls to lose. It's just the number of rolls in the game of craps, win or lose. So win or lose, you have a 1/3 chance of stopping after the first roll. Now, n equal 2, the game stops on roll 2 if the point is in one of these 6 numbers on roll 1, meaning we didn't win or lose instantly. And on roll 2, either the t, the point, or 7 is observed. So let's calculate that. And here's a note. The probability of 4 and 10 have the same probabilities. 5 and 9 and 6 and 8 all have the same probabilities. So that's what this 2 out front in each of these terms are. That's because we're only going to do this for 4, 5, and 6, and then take each times 2, and then that's the same as 8, 9, 10. So the probability that we roll a 4 on the first roll is 3 out of 36. The probability we roll a 4 or a 7 is 3. There's 9 ways to do that over 36. So this is the probability that the game stops if we had rolled a 4. Now a 5, there's 4 ways to roll a 5 on roll 1. And there's 10 ways to roll a 5 or a 7. And so this is the probability. And then this is the probability for a 6. Roll a 6 and then roll a 7 or a 6 on the next roll. So that's roughly a 19% chance that happens. The game stops after 2. So the probability that the game stops on 1 or 2 rolls, you just add those up. Now, n equals 3, the game stops on roll 3 if the point is in one of these numbers on roll 1, meaning we didn't win instantly, not a t, not the point or 7 on roll 2, and either the point or 7 on roll 3. Okay, and again, 4 is the same as 10, 5 is the same as 9, 6 is the same as 8. So we're just going to take each of these times 2 and calculate it for 4, 5, and 6. So the probability we roll a 4 is 3 over 36. The probability that we do not roll a 4 or a 7 on roll 2 is 27 out of 36. And then the probability that we roll a 4 or a 7 on the third roll is 9 over 36. And then you can do this for 5 and 6. These are the calculations. And there's a 13% chance that we stop on roll 3. Now, going 4, 5, and 6, it's actually, we can just use this formula that we just derived. So on roll J, and actually J can be 2, 3, 4, or 5, anything above 2 or more. The game stops on roll J if the point is in one of these on roll 1, meaning we didn't win instantly, not a T, not the point or 7 on rolls 2 through J minus 1, and either the point or 7 on roll J. Okay, so what that means is that if we look at this, so 3, 4, and 5, we're summing it for 3, 4, and 5 because we're summing it for 4, 5, and 6, which is the same as 8, 9, and 10. But when we're associated with 4, it's 3 ways that can happen, and when we're at a 5, there's 4 ways, and we're at 6, there's 5 ways. So that's kind of why we see 3, 4, and 5 here, because that's this number in the front, right? 3, 4, 5. And then this is the number of ways that we can not roll the point or 7 on rolls 2 through J minus 2. And then this one, I plus 6, is the way that we can roll the point or a 7. And this is again for dice 4, 5, and 6. And then you can just multiply this out and it becomes this number here. Now to find the mean, so this is the probability that we stop on roll J. This is it. So to find the mean number of rolls per game, meaning the expected value of n, we take 1 times the probability that we stop on roll 1 plus 2 times the probability we stop on roll 2, 3 times the probability we stop on roll 3, etc. It goes to infinity. Well, let's plug in P of J here, and it's this. And this is it. This is the number. So you can either, pick a really, not infinity, but a really large number and get really, really close to it, or we can derive the exact, and that's what we're going to do. But we have to do it in piecemeal. So we'll derive the first term of this infinite sum. So if we look at this term here, it's actually this first term, right? 227 raised to the J minus 1 over 36J. This is the first term. Now, the 2 we're going to bring out front. The minus 1, the 27 minus 1 is what this one is. We're going to take it out of that product and divide. And then we're left over with this. And going from this step to next step, it requires a result from this video in my playlist or in my channel. It's called Alternative Formula for the Expected Value, where we derive alternative formulas for the expected value when it's continuous, x is continuous, or discrete. And so going from here to here, after you watch that video, you go, oh yeah, that totally makes sense. But it's just mind-boggling that these two results are the same. And so you'll have to trust me that they are. But after you watch this video, it's instant that you know that this is correct. Now, these infinite sums are geometric series, right? So this first term is here. Second term is this one, right? Starts at 3, so it's to the third power. Starts at 4, it's this one. It goes on forever. Now let's take out the constant denominator, which is 1/4. Bring it up, and that's the 4 times 2 is 8. And then we get 2 times this number. But then we have another geometric series starting at the third term, 4, 5, 6. And then that is again this. Remember, we're already taking out the denominator. Well, this can be calculated. This is 5/6. Now, back to the expected value of n. If we just, so what the first term, it's 1/3, and then this is the 5/6 is the first of the three infinite terms, and then these are the next two, and I'm hoping that you go through the same math and derive it. But this is 3.375 with a vinculum above it, and this is it. So the average number of rolls is about 3.4 per game, win or lose. That's it. Now, quick simulation in R is we create this function called craps. In roll 1, we sample 2 observations. We check to see if we win or not. If not, we go to roll 2 and we just keep rolling until we see our point or a 7. And then we list out the results. And so let's play it. So craps, it looks like we win. Our point was 8, your number. Took 5 rolls and we stopped because we rolled an 8. That's why we won. Play again, we win. My number's 7. So that means, yeah, 1 roll, we won. We stopped because we rolled a 7, we win. Here we lose. Our number's 2 on roll 1, and that's an instant loss. So that's why we stopped, because roll 2. Now, let's simulate this 700,000 times. Boom, store the results and outcome. And the third row contains the number of rolls. So let's just calculate the mean. So it's 3.375, which is really close to the theoretical result. And of course, the larger the n goes, the more accurate this is. Now, one thing here, this function, I'm actually using it to study other aspects of the game craps. Okay, so I'm outputting 4 pieces of information here. If you only were interested in the mean number of rolls, you perhaps should only output the number of rolls, and you don't have to save all this extra information. So it outputs just a vector of the number of rolls. You take the mean, boom, done. And it's going to be so much faster than the function that I created. But mine carries a lot, more information that I'm going to use potentially in other videos. Okay, we're at 12 minutes. I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.